Hello, and thank you very much for joining our webinar today. My name is Anastasia Papas, and I'm the founder of the e-Access Forum. It is a great pleasure for me to welcome Jean-Paul Renne today, who will present his paper with Pauline Chicani, Climate Linkers, Rationale and Pricing. Jean-Paul is a professor of economics at HEC Lausanne, which he joined in 2015. Previously, he worked as a senior economist at the Banque de France and as the head of operational research at the French Debt Management Office. He has a PhD in applied mathematics from Paris Dauphine University. His research focuses on time series modeling with applications to the dynamics of interest rates, the pricing of disaster risk, and public debt management. He has published articles in the Review of Economic Studies, the Journal of Econometrics, Management Science, and the Review of Finance. But as always, and before I pass the floor to Jean-Paul, I would like to invite you to answer the couple of survey questions that you are going to see now on your screen. So the first question is, do you think market expectations regarding climate can be extracted from existing financial instruments? And the second question is, do you think green bonds can be used to hedge against a climate risk? Okay, so just a few seconds. Well, it seems that the majority thinks that market expectations regarding climate can be extracted from existing financial instrument, but only somewhat. And for the second question, the majority, 67%, thinks that green bonds cannot be used to hedge against climate risk. So now, Jean-Paul, that you know what the audience thinks, the floor is yours.
Thank you very much, Anastasia, for the introduction. So let me share my screen, my slides. Okay, so I'm very pleased to be here. Thank you for inviting me to present here. So this is joint work indeed, as you mentioned, with Pauline Chicani, who is also at the University of Lausanne. So okay, so in this paper, what we do is that we consider this a potential hypothetical novel class of financial instruments that we call climate linkers. And these climate linkers, they would be bonds or derivatives like swaps or options with payoffs that would be indexed directly to climate variables. Okay, so for instance, we could have a swap indexed on temperatures or indexed to sea levels or that kind of thing. So by construction, these instruments, they would provide a hedge against climate risk by construction, right? And so in that sense, they would be different from what we have on the financial markets currently. Okay, so typically, and it relates to one of the two questions. So here, the green bonds, they obviously also relate to climate, but not as hedging instruments, right? In the sense that the payoffs of green bonds, they are perfectly conventional payoffs, right? It's just that the funds are not used the funds of the proceeds. When somebody issues a green bond, the proceeds have to be used for mitigation projects, but the payoffs of the bond, they are like standards. We also have, so these climate linkers, they would also be different from weather derivatives. Because in the sense that, so there is already a fairly small market for weather derivatives, but usually these instruments, they have short maturities, so of maximum of a few months, and they are indexed to local risks. So say rainfall in a given state of the US, things like that. Okay, so what we have in mind here for these climate linkers, that would be the payoff, the indexation variables. They would be global variables like the global mean sea level or global surface temperature. So in a way that they could be used to hedge against global risks, and the maturities would be large. Okay, so we have in mind years or even decades as maturities. And yeah, so in this respect, so these instruments, they would be different from what already exist. Also, they would be different from the sustainability linked bonds, because these bonds, basically the payoffs, they depend on something that relate to climate, but it's more about the performance of the issuers with respect to some indicators that relate to the efforts that they can make to mitigate. So something like their CO2 emissions or things like that. But these payoffs, you see that they cannot be used. So these bonds here, the payoffs depend on climate-related variables, but they cannot be used as hedging instruments against climate risk, because they are very specific as a random variable, say. So in the paper, so we discussed the potential advantages that we could see in that kind of instruments, and what we also do is that we propose a model, a tractable model that would make it possible to price that kind of instruments. Okay, so that's going to be an integrated assessment model. And we're going to make some efforts to have something tractable here, in a way that with this model we'll be able to compute temperatures of typically temperature swaps, for instance, or the temperatures of options. And we're going to use this model to explore climate risk premiums. Okay, the climate risk premiums, like generally speaking, they correspond to their risk premiums that will relate to climate risk. So a risk premium, as a rule, is something that we have in prices of financial instruments. And the risk premium is, in a way, it is the part of the component of these prices that would not exist if agents were risk neutral. Okay, so if agents were risk neutral, we would not have any risk premiums, and the prices that we would observe of the market would just be the expectation of the agents regarding future variables, without risk adjustment. But as soon as the agents, they are risk averse, when you have an instrument with a payoff that depends on the risk that towards which the agents are risk averse, then in that case, in the prices of the traded instruments, we have credit premiums or risk premiums, which correspond to the extra yield that is asked by investors to be compensated for typically taking a risk when buying these instruments. So in our case, of course, because we will have this by construction, the climate linkers, they are going to relate a lot to climate risk that people do not like. We expect to have climate risk premiums in the prices of these climate linkers. Okay, so just to fix ideas, let me explain how a temperature indexed swap would work. Okay, so that would be a swap, a typical standard swap, except that the payoff would depend on temperature. Okay, so assume that we're today on day T, and then we have a maturity of H. which means that the payoffs are going to take place on date t plus h. Okay, we'll have at the end of the swap, we'll have two payoffs, because in the context of a swap, we have two counterparties. We have a protection buyer and a protection seller. And so the protection buyer basically says on date t to the protection seller, in H period, okay, so at maturity of this instrument, I'm going to pay the fixed leg of the swap, which is equal to TS, the temperature swap, multiplied by a given notional. Okay, and this temperature, the temperature swap, is negotiated on date T. And the protection seller, he says on date T to the protection buyer, okay, at maturity, on date T plus H, I'm going to give you the realized temperature on date T plus H multiplied by the notional. Okay, meaning that in the end, at the maturity of the swap, T plus H, if in the end, the realized temperature is equal to this temperature that they had negotiated on date T, then the two payoffs are going to be equal, and there will be no net payoff at the net payoff is going to be zero at the end of at the maturity of the instrument. By contrast, if typically we have particularly large temperature on the T plus H, realized temperature, then the protection seller is going to, in net terms, the protection seller is going to give a positive payoff to the protection buyer. Okay, so you see here with this example that if we can easily understand that if agents, they were risk neutral in that context, in the context of these swaps here, then we would have that today, the swap that would be negotiated, the temperature swap, would be equal to the expected temperature. Okay, so if the agents were risk neutral. But then as soon as you are in a context where the agents, they are not risk neutral and they don't like the climate risk, they don't like unforeseen increases in the temperature, then in that case, you would expect the temperature swap to be higher than the expected temperature, because basically it corresponds to the story that the protection seller is going to say to the protection buyer, okay, I'm willing to give you the realized temperature on date T plus H, but only if, so I'm going to take the risk, the climate risk, but I want to be compensated for that risk because we don't like it. Both of us, we don't like that risk. And so I want you to provide me with not only the expected temperature, but with a small premium, an insurance premium that here in that specific case, we're going to call climate risk premium. So, and the model that we're going to propose here is going to, the objective is going to kind of to gauge this the potential credit risk premiums that we would have in these instruments. Okay, so of course, as any derivative, these climate linkers, they would allow for sharing risks across different agents. So by entering a climate linker market, the agent, they could share the climate risks. But also so some advantage that we put forward in this paper for that kind of instruments is of the information type. So if we had that kind of market, a liquid market for these climate linkers, that means that looking at the prices that would trade today, typically this temperature swap that I presented before. So today we would observe, potentially for different maturities, different age, we would observe the temperature of temperature swaps, and this would reveal up to the climate risk premiums. This would reveal the expectations of the markets regarding future temperatures, and this would be time varying, right? That would, if we had liquid markets, this would be time varying. So from one day to the other, we could see whether these expectations of the markets regarding climate trajectories, do they move in one or the other direction? So typically, for instance, this means that if we had that kind of instruments, consider that day where we have an international summit on climate, and so you have different governments that meet and that try to take some decisions, some measures, comparing the prices of the swaps before the meeting and just after the meeting, we could get a sense of the credibility of these new measures that will be taken as tools to fight against climate risk, right? So if typically just before and just comparing the temperature swap before and after the meeting, if we see some decreases in the temperature swap, that would mean that the market to seem to believe that these measures are going to have an effect on temperatures. Okay, we could see that. So for those who are familiar with that kind of instruments, so that kind of informational advantage is widely used, for instance, for the inflation derivative market. Okay, so you have a lot of people looking at the prices of inflation derivatives just before and just after the speeches by central banks to see whether the policy measures, the monetary policy measures, are have according to the market will have according to the market an effect or not. Okay, and on top of that, also still regarding this informational advantage. So the kind of advantage that we could have with that kind of market is that we could, this would definitely help to calibrate these integrated assessment models that we have. Okay, so because consider, for instance, the social cost of carbon. Okay, so there are many papers that try to estimate the social cost of carbon. For the time being, if you want to compute social cost of carbon, you will need a kind of model. So typically of the integrated assessment, an integrated assessment model. And this model, you will need to parameterize it. You will need to using parameters from natural science or the economic literature if you need to put risk aversions or things like that there. And you will use this model to compute social cost of carbon, right? Now, assume that we have a climate linker market. What you could do is to use the climate linker prices that we would see on the market to try and improve on the parameterization of the model. Okay, in a way that you would, okay, if you can, with that model, if you can compute model implied climate linker prices, you could look for the parameterization of the model that makes it possible to fit these prices here, and then doing so, you would be able to compute some kind of market augmented social cost of carbon. Okay, so that's the kind of thing that we could do as well. Okay, let me now present the model that we have in mind. Just before that, to be sure, right? So here, to provide you with the spirit of the study here, we explained that we could have these climate linkers and they would have different advantages. Now, these climate linkers, for the time being, they do not exist, right? If they existed, we could just, we wouldn't need a model to study climate risk premiums, because basically we could maybe observe these things more easily just looking at the market prices. But we don't have the market prices for the time being. So if we want to have an idea of what these climate risk premiums they would be, so we need at that stage to use a model, right? Again, if at some point, coming back to my previous idea, if at some point there is something like a liquid market for climate linkers, then we could use this data to improve on the parameterization of our integrated assessment model. But for the time being, the outputs that I'm going to present in terms of climate risk premiums, they are 100% based on the integrated assessment model. Okay, so the model we use here is an integrated assessment model, and meaning that it belongs to this family of models that was initiated with the DICE model of Nordhaus. This is a stochastic model, of course. Otherwise, if it was not stochastic, it would not be possible to compute risk premiums, of course. So there already exists some stochastic integrated assessment models in the literature, but the one that we propose here is particularly tractable. Okay, meaning that we can solve it like in a very fast way, and not only that, but we can, once the model is solved, we can use it to compute very fast, in a very fast way, again, some prices for any climate linkers at any maturity. Okay, so the trick here is to use that kind of affine model. So basically what we do is that we tweak, change a few equations of the standard stochastic dice models in order to have a conditionally affine form. This kind of trick is already used by Traeger in a couple of papers, but here we show that we can use, once you have that kind of affine model, you can also use the affine property of the model to compute any conditional moment of the state variable that you have in the model. So that's what gives the tractability, and this tractability used for two things: to price our climate linkers, as I mentioned before, but also to calibrate the model. Okay, in the sense that with this model that is very fast to solve and to we can easily compute any conditional moment for the state variables that we have in the model. And so if we really want the model to fit that specific expectation of temperature at that given horizon, we can make sure this is going to be the case. Okay, so that's also why it's important for us to have a tractable model. Okay, so briefly, the overview of the model, that's an integrated assessment model. So that's what I'm going to present now, is something that is not specific to our model, but that is shared by the different integrated assessment models. So we have production, we have an economy here, and goods are produced. And these produced goods, they can be consumed, or they can be used to invest in the production technology. But it can also be used to, part of it can be used to invest in mitigation project. Okay, if we invest a lot in mitigation project, it means that for a given amount of good produced, we will issue less CO2. But if we don't invest in mitigation project, then it means that to produce a given amount of goods, we will need to issue a lot of CO2. Okay, and if we have higher CO2 emissions, then it means that we'll have higher temperatures. And the specificity of our model is that we incorporate these feedback effects here that go directly from temperature to CO2 emissions. The idea is to try to capture this tipping point phenomenons. You see the standard example of that would be like permafrost. So if we have higher temperatures, we increase the probability to have big release of the CO2 that is currently trapped in the permafrost in Siberia. Meaning that CO2 emissions, they do not only increase in the atmosphere because we produce, but they may also come just from increases in the temperature itself. Okay. And if we have higher temperatures, it means that we will have higher damages, and these damages are going to negatively affect the production process. Okay, so I won't go in details across all the equations here. I'm just going to highlight a few ingredients that are important for our model. So the first one is the way we model damages here in this model. So damages is going to be this dt variable. And the damages that we have, they show up in the capital accumulation equation. Okay, so we use this trick here that has been used that has been introduced in this couple of papers. We consider that the agents in the model, they have a planned capital, so that's the capital that they would like to have on the next date. Okay, so it's going to depend on the investment you make and on the previous capital, and you have depreciation. But then on the next date, in the end, it's not going to be K star that you will have, it's going to be K, and K may be larger than K star if capital D is positive. Okay, so D is going to be something positive. It can be equal to 0. If it's equal to 0, it means that you don't have that planned capital is equal to effective capital. But if you have D is for disaster, if you have this disaster, so if D is positive, then you will have a destruction of capital. And so next period, you will be able to produce less. Okay, and this D is going to be drawn in a gamma 0 distribution. The important point is to see that, okay, this T80 here, that's for atmospheric temperature. And so it says, basically, this equation here, it says that when we have higher atmospheric temperature, we have a higher probability of having disasters, okay? Because this thing here, LD0 plus LD1 T80, it corresponds to the probability of having a positive D. Okay, and then the other equations that we have in the model, they are fairly standard. The only thing is that we have to linearize a couple of these equations, because remember, we need to have, we want to have an affine model. So we need to linearize a couple of equations, in particular, this equation that relates radiative forcings to carbon concentration. But as suggested here on that chart, so you see the upper chart here, it shows the dashed line, it corresponds to the linearization that we use in the model. The solid line corresponds to the non-linearized version of this equation. You can see that for the plausible values of atmospheric concentration that correspond to the gray areas, this linearization is not has no strong effect. Okay, and so let me just explain here how we do quickly to model this tipping point that we have in the model. So basically, we just say that there is this NT variable that goes from temperatures to emissions. And so meaning that when T is large, temperatures are large, we increase the probability to have positive draws of NT that would increase the stock of emissions, or the flow of emissions for that period, sir. Okay, just a brief presentation of the model, and then this in our model here. So what is interesting is that, again, thanks to this affine property of the model, that's easy to solve the model, meaning that even if we specify this kind of preference for the agents, so the agents, they are risk averse, they don't like climate risk. And so here we say that the preferences of the agents are well described by Epstein-Zinn preferences. So we have elasticity, unit elasticity of intertemporal substitution, a risk aversion gamma that is strictly larger than 1. And so we can solve for the model, meaning that we can deduce from the model specification the process that's going to be followed by consumption in that model. And you see that here, when we solve for this, we obtain that consumption is going to be affected by DT. DT was the disaster, the climate disaster that I mentioned before. Okay, so if we have some disasters, it's going to reduce consumption. Okay, and then just what we have here is just a statistical object that is called the Laplace transform of xt. Xt is our vector of state variables. So in xt we have many things. I think that the dimension of xt is like 12 or something like that. So in particular here we have macroeconomic variables like consumption or GDP, and on top of that we have the climate variables as well. So we have temperatures, atmospheric temperature, the ocean temperatures, carbon concentrations, and we also have sea levels in there. Okay, we have sea levels. So there is okay, let me just explain how we managed to have sea levels in our model. So in standard integrated assessment model, there is no sea level. But what we have noticed is that there is this literature that says that the sea levels, we can find some so-called semi-empirical models where the sea level depends on temperatures. Okay, so we can find that kind of equation in the literature, and so we just add this equation in the state space that we have in the model that we have, and once sea level ht is in the vector of state variable, it means that we will be able to the model can be used to price instruments that are indexed on sea levels. Okay, and so okay, so once we in the tractability of the model, it comes from the fact that the Laplace transform of xt, the vector of state variables, is exponential affine in xt. And so this AT and BT function, we can we have expressions for these functions. Okay, so once we have that, it means that we can compute many things. In particular, as I mentioned before, we can typically compute the model implied conditional expectations of temperature in 200 to 2100. Okay, so we can compute this very easily. We have formulas for that. We can also compute this according to the model, what is the standard deviation of temperature in 2100. Can compute different moments like this. And so, you know, in the model, there are many parameters that are common. So in the DICE, many of the parameters we have in our model, they are also in the DICE model. So we can just take the same parameters, but there are a few parameters in our model that are not in the DICE model. So typically, you know, the specification of damages. Okay, I mentioned that damages that depend on the probability. The probability to have disasters depends on temperatures, and we had this L parameter that say how the probability depends on temperature. So these parameters are not standard. So, but what we do is that we make a list of targets, so some moments that we would like our model to be consistent with, and we look for the parameterization of the model that make our model consistent with these targets. Okay, so you see that typically this expectation of temperature in 2100. So we have this target that is not optimistic, and we just this target here correspond to this RCP scenarios of the IPCC. So we take this target 3.50 degrees on average temperature anomaly in 2100. If we're not happy with that value, we can definitely calibrate the model with another value. So of course, the results that I'm going to present, they would be different, but that's something that is super fast to do in our approach. And so on this model implied column, you have with the calibration that we have, trying to look for the parameterization that gives the closest fit for all these targets here. So that's what the model that we parameterize in the end is able to achieve. Okay, so you see that we have fairly good properties for in terms of fit for this model. An important parameter that I would like to highlight here is this parameter minus 0.12. That means that the specification we have implies that an additional degree on the temperature anomaly would result in a decrease in consumption by 12%, according to our calibrated model. This is based on this work here by Burke and co-authors. Okay, so now let me jump to the climate linkers again. So we have this calibrated this model. So we can use this model to price the climate linkers, okay? And we can do this in a simple way because we have an affine model. So let me jump directly to some figures. So here you see some model implied moments and prices. Okay, if we look on panel A, here you have in the blue line correspond to the model implied expected trajectory of temperature until 2100. Okay, the dashed line, they correspond to IPCC scenarios. And we have the blue shaded area, they correspond to presence intervals that we have in our model, because our model recognizes that temperature is going to be uncertain, right? So it's going to be affected by shocks. And so the model recognized that as of today, we don't know perfectly what's going to be the temperature, and this corresponds to confidence intervals according to the model. So that is for what I'm going to call the physical expectation of temperature. Now, in orange, we have temperature swaps. Okay, so you remember these swaps that I presented at the beginning of the presentation. So they would be if we have the protection buyer, protection seller, and I explained that if these agents they are averse to the climate risk, then you expect the temperature swap, to be higher than the expected temperature. And so the model is consistent with this story, and it says that okay, the orange line would be, according to the model, the temperature swap that we would observe according to the this more calibrated model on the market. And you see the difference between the orange and blue line correspond to the climate risk premiums. So typically it says, for instance, that even if these two agents, protection buyer and protection seller, even if they agree on the fact that the expected temperature in 2100 is 3.3, maybe that they will also agree to have a temperature swap that is equal to 3.5. Okay, because the protection seller is going to the protection buyer is going to be willing to pay to make a loss on average to be insured against climate risk. Okay, the difference between two is a climate risk premium. Okay, so we have the same kind of stories for sea levels. Okay, we could have also a swap on sea levels, and here we also see that there would be also a climate risk premium on that kind of market for sea level swaps. And let me end with these options. Okay, so we could also have climate options. And so an option is a financial instrument with a maturity and a strike, right? So let me just focus on the red lines that would correspond to a strike of 3 degrees. Okay, TK here is expressed in degrees, so that would be the strike of the option. And then we have maturities. So typically for maturity 2060, and an option with a strike of 3, this digital option, the payoff of the digital option would be the following. If on 2060, temperature is higher, the realized temperature that we will observe in 2060, if it is higher than 3 degrees, then this digital option would give 1 to the option buyer. By contrast, if in 2060, the realized temperature is below 3 degrees, then the payoff would be 0. Okay, so if you have something like this, the price today on day T in 2023, the price of that instrument, it can be directly interpreted as a probability. Meaning that here, this for 2060, T a strike of 3, we have approximately 20%. Okay, meaning that means that the risk-adjusted probability of having temperature in 2060 higher than 3 degrees would be equal to 20%, according to the calibrated model. The dashed line corresponds to the physical probability, according to the same model. Okay, and so we see that the physical probability of having temperature higher than 3 degrees on 2060 would be 10%. Okay, so again, the difference between the physical probability, 10%, and the risk-adjusted probability, 20%, is an expression of climate risk premiums. Meaning that according to the model, because in the model, the agents that don't like climate risk, they are willing to buy these digital options, even if they, when buying so at a high price, 20%, they know that on average they will make a loss. But because these options that provide them with an insurance against disasters, very high temperatures, they are willing to pay this insurance premium. Okay, so this brings me to the conclusion. So in this study, in this paper, we consider these climate linkers that would be financial instruments with payoffs indexed to climate-related variables. So in the paper, we discuss potential advantages of these climate linkers. So here today in the presentation, I stressed the informational advantage that we could have with these climate linkers. And we also propose in the model a tractable integrated assessment model that could be used to price these climate linkers. And we exploit this model to discuss climate risk premiums that would be this specific part, the specific components of climate linkers that would correspond to insurance premiums. Then to end with, what about the potential for having such a market in the coming years? So here, I unfortunately I need to be a bit not completely enthusiastic about potentially a launch for this new market very shortly, because that would require a lot of political will to launch that kind of market, in the sense that launching this market would be costly for the first issuers. So typically, if assume that some governments they want to push for that kind of climate linkers market, they would need, that's very likely that to do that, they would need in the first place to issue climate linker bonds. So we would have government bonds that whose payoff would be indexed to climate variables. And that's only if we have the government that start to issue big amounts of these things that we could imagine having a liquid market with derivatives developing afterwards. That's what happened for the inflation market. For the inflation market, you know, we now have some inflation derivatives, but we have these inflation derivatives because in the first place, more precisely in the 90s, governments started to issue inflation-linked bonds. Once you have these inflation-linked bonds on the market, so investors, they get to know how to price these things. And once the banks, big banks are familiar enough with the pricing of this instrument, they start proposing to their clients some derivatives with payoffs indexed on the same type of variable, typically inflation in the 90s, right? And so meaning that again to have the development of such a market, my feeling is that we will need in the first place to have big issuances of bonds by big issuers like governments. And these big issuers, they would be, I said that they would need to have political will to do that, because in the first place, launching a market is costly, and it has been shown in a few papers that typically the launch of the inflation-linked bond market was costly for the governments, in the sense that in the first few years, maybe there was something like mispricing, and meaning that the typically inflation-linked bonds for the first few years, maybe they were not traded at a sufficiently high level. Meaning that the issuers, they were facing some novelty premium, so they were losing money on average because of this novelty premium. Okay, so I'm going to stop here. I'm very happy to take questions.
Thank you very much, Jean-Paul, for a very interesting presentation. I would like to invite you to post your questions on the Q&A function. So we have one first question. What underlies besides sea level increase are you considering? And how hedgeable are they? Are there counterparties who are willing to enter the opposite side of these hedges?
Right, good point. So for sea level, so sea level, so basically so the way we model it is just that we borrow from this literature with that try to find a way to model the joint dynamics of temperature and sea levels. And so once we put it in the state vector, so meaning that we can price, we have some conditional distributions for sea level, and so we can also price these instruments. Regarding the buying side, the two sides of these instruments, that's a very good question. So through the lens of the model, okay, because here we have this model. So the model, if you want, and it gives an idea of what we have in mind here. The model says that, in the model, there is only one representative agent, or an infinity if you want, but they are all the same. They all have the same expectations. They all have the same, they see the world in the same way. but they are all risk averse. So none of them like climate risk. So that's why when they want to trade stuff that relate on that are indexed on climate risk, so that's why we have risk premiums, because none of these agents is happy with taking the risk associated with climate. So if two of them meet and want to trade the swap, basically they are going to look for an equilibrium price that will make them both indifferent between entering the swap. Okay, so that's the spirit of the model, meaning that, and that's why the protection seller says to the other one, okay, none of us like the climate risk, and so which okay, in the world not many people are happy with climate risk. So we both know that. So I'm willing to provide you with the insurance, but only if you provide me with a positive excess return. Okay, that's the philosophy. So that in the model here, that's the spirit. Now, if we move away from the model here, we could imagine still that there are maybe some situations where some people are more willing to take a climate risk than others, countries that are more or less exposed than others. So in that case, we would have motives for trade, like a more natural motive for trade. In that case, maybe that if we had that kind of model, it's not the case here in our model. We could try and sophisticate the model with having heterogeneous agents that are more or less exposed to climate risk. In that case, the concept of, or the computation of risk premiums would not be exactly the case, because we would maybe that some people would be happy to insure the other ones at a lower price, things like that. But indeed, for sure, in all cases, you would expect to pay, even if you have heterogeneous agents. In the end, we would certainly have some positive climate risk premiums, in the sense that on aggregate, people are not going to like climate risk. So we would need this climate risk premium to account for that.
Thank you very much. I have a question. Through your model, you estimate the social cost of carbon to be at around $1,500. Most of the literature, at least I have seen, is places the social cost of carbon anything between $150, $185 to $300 per ton. I was wondering if you could talk a little bit about why your model generates such a high social cost of carbon.
Yeah, okay. Yeah, of course. Thank you for this question. That's an important point as well. Indeed, we have in the estimate that we put for the time being in the paper, so we have very large social cost of carbon of $1,500. That's very high compared to other estimates, and we're currently recalibrating the model, and the estimate is going to decrease substantially, because the thing is that there are two important points to account for that. The first one is that maybe not, I'm going to show that. The first one is this thing here that I mentioned and briefly, which is large compared to the other damages function that people use currently in integrated assessment model. So here we say that an additional degree, degree in temperatures by 2,100 would decrease consumption or output by 12%. This is larger than what many models say these days. Okay, so that's the first ingredient, because we say basically that climate risk is very large. So that's first point. The second point is this tipping point thing that we put in the model. So as I mentioned before, we try to augment the standard integrated assessment models here with something kind of positive feedback loop that goes from temperature to CO2 emissions. And so we took from the literature some estimates of the of carbon that would be trapped in the CO2 carbon that is trapped in the permafrost. And so we try to calibrate the model to reflect these estimates that we have in the literature. And so when you do that, indeed you make you increase the risks associated with temperature by a lot. And so meaning that as soon as you allow for this tipping point effect, you increase a lot the fat tails of the distribution, if you want. And when you do that, of course, you make things a lot worse regarding climate, and so that's why you increase a lot the social cost of carbon. That says that basically, okay, if you decrease the carbon in the atmosphere, that has a very large value for welfare. So that's because of it. This being said, again, as I said before, because we feel that indeed these estimates are very large compared to what we have in the literature. So we are going to elaborate on that point, and what we want to do in particular is to show how in a follow-up paper how this tipping point effect has a huge impact on the estimate of the social cost of carbon.
Great. Thanks a lot. One more question. You suggest that these climate linkers have two advantages. One is the sharing of long-term climate risks, and the other is that through the transactions, we can understand the market expectations about climate risks. There are three types of instruments that you are suggesting: the swaps, the bonds, and the options. And my question is, are all three equally efficient in providing these two advantages, the sharing of the climate risk and the informational advantage?
Okay, so thank you for this question. So yeah, I think that it really depends on the kind of risks we want to hedge against or we want to get information on. In the sense that the options, okay, let me jump there to this temperature. See here. So you see the options, they're going to tell us about in terms of information and then also in terms of hedging. That's the thing. They will tell us about the probability of disaster risks, right? So typically T equal to 4. Okay? So that's the probability of having temperature higher than 4 degrees. So if you really want to get what the market thinks about this kind of disastrous event, then you would need to we would need to have some market for climate linkers with high strikes. The same for the hedging property. If you want to have a market that makes it possible for people to share risks, extreme risks related to climate, then you would need to have an option market with large strikes. So the options, meaning that the options, they are more about like extreme events. Then the swaps, swaps, they are they give you an indication on the middle of the distribution. Okay, so that's what we had here, for instance. So you see the swaps, they correspond to the orange line I mentioned, that correspond to the swap rate according to the model. And so basically it tells us about the middle of the distribution. So meaning that if you want to be hedged against moderate risks, moderate climate risks, then you would go for swaps maybe.